can say, extend this out, and then you have like Z patterns going on, right? So that means this angle is going to be theta, this is going to be 180 minus theta, this one would be theta, and then 180 minus theta is this one. Okay. All right, ready to keep going? Third dimension? Okay. There is one part of this lecture, and I apologize that I'm going to leave out, which is drawing 3D vectors. For two reasons. One, because I believe computers can draw 3D vectors better than humans can. And secondly, because I can't draw a 3D vector. So I'm not going to require you guys to do so. So basically what a 3D, I'll talk about what it should be though to look at, but it's very difficult to draw. Here we go. Three-dimensional vectors is sort of title today. We're going to say if ABC is a 3D vector, we're going to let I equals 1, 0, 0, J equals 0, 1, 0, and K equals 0, 0, 1. These are the unit vectors. I'll get rid of the way here in a sec. So anything you can do with a vector, you can also do with algebra, and that's what we're going to get into. How'd the hockey game go for? Is it 3-0 or 2-1? If you don't know what I'm talking about, the rest of the class don't want to go okay. The point is here, what we did is we turned these unit vectors then. So again, just like before, we had a two-dimensional vector, we had I and J. For 3D, we're going to just add K in there as well. Okay? These are the unit vectors. That's a unit vector, remember, has a distance of 1. We can change any Cartesian three-dimensional vector then into algebra, which is what part of this is going to be as well too. Okay. So all today's lesson will be is extending what we know about two-dimensional vectors into the 3D. There won't be anything new. We're going to do finding theta. We're going to be doing all that stuff again in the third dimension. You can imagine yourself, we're going to stop probably at 3 dimensions this year. When you get to math in university, they will go higher. You'll say, what is a 5-dimensional vector? Well, I can't see it either, but it's useful for making phones. That's all I can tell you. Why, I don't know, but it is. Okay, right? So there's things that are not necessarily tangible, but they'll be useful for. Here we go. The magnitude of a Cartesian vector. I'm not going to prove this for you. I'm just going to give it to you. So if U is equal to ABC, the magnitude of U is equal to the square root of A squared plus B squared plus C squared. So the same way, let's get over here. So the same way that we dealt with, the distance over here of two-dimensional vectors is just the same thing as that gets thrown in there as well. Okay, I'm going to deal with 3 more notes and then we'll get to some examples here.
Are those like, going back to the previous page with AI, EJ, CJ, are those vectors like with the arrows on top of them?
No. No. I guess technically it is, yes. The I, the J, and the K would be. Thank you, yes.
Just wondering.
Yeah, thank you. Sorry. We're going to say vector addition. simply enough, if I have u is equal to ux, uy, uz, I'm going to add to this w equals wx, wy, wz, u plus w. You just add components. I know, surprising. So again, nothing new. I just have to show all these rules again in the third dimension. We've already done. And finally, a vector between 2 points, which is what we used in last night's homework, and we'll have to use again today. So once again, if I have u is equal to ux, uy, uz, and I have w is equal to wx, wy, wz, the vector uw, oops, equals wx minus ux, wy minus uy, wz minus uz. Okay, so we'll deal with this like sort of just like usual. I gotta get the silly notes out of the way here, and then we'll do examples the second half. So this is the same thing that we did in the last example with the parallelogram. Okay, right, where you dealt, it's the second point minus the first point. That's what if you find a vector between 2 points. Now, the nice thing is everything we learn in 2 dimensions, you can also do in 3 dimensions. Okay, we can do the vector, all the word problems. Work sort of less so, but you can do the projections, you can do the angle between 2 vectors. All the stuff's the same. The formula is the dot product. Nothing changes in 3 dimensions compared to 2. Let's do our first example though, and then we'll get on to the dot product. Okay, I'm going to get out of the way right now, and we'll go through this one as a class. You guys can just pull that down. I can't remember where I stopped or even started here. I'm going to start in the back row. So Jason, even though you've been sick for the last 2 days, you're going to pick on you momentarily once you write down that question. Okay? Yes, we have in 2 dimensions. Okay, this is the thing. A lot of today's lesson, you're going to be so bored today, Bailey, because today's lesson is just it's the same thing we did in the 2D, but it's going to be just with 1 extra number with it. That's the only difference in that. So I didn't mean to say bored.
What's W? I can't see it.
Oh, 1, 4, negative 3. Okay. Jason. Can you be brave for me, please? And tell me what negative 3u would equal. Very good. Brendan, can you tell me please what v we already have, so I'll write that down. Can you do negative 5w for me in a second? Go ahead, negative 5W, please.
Negative 5, negative 3.
I didn't hear you, but I think that said 15, I think is what you said, right? Nope. Okay. I just wrote them out like that. There are people in this class that are going to say, Mr. Sadler, my brain is this big, I don't need to write that out, and that's fine. I like to have it lined up like that, because then you can just add them. So when I add up all those together, I'm going to call it R to make it easier. Can you be brave, please, Teresa? And add those together for me, please. Well, we just got to add the components, right? So just did yeah, so it's going to be negative 16. Negative 12 minus 20 is negative 32, and 1 is negative 31. And 15 and negative 15 is 0 and 6. Okay. So I just hopefully added that up correctly. Can someone confirm that for me? So my brain isn't 100% going here today. All right, Austin, using your giant brain, can you tell me please how to find the magnitude of R? Pause. Okay. Yeah. Right? And that's all it is. You guys go back, stay with me here, please. So root of negative 16 squared plus negative 31 squared plus 6 squared. Chris Wee, can you be brave and get your calculator out and calculate that for me?
So then, square root of 256 plus 961 plus 36.
Okay. Can you add those up for me?
Yeah. And that's 1,253.
I think that's a prime number, I'm guessing. I'm okay to leave it at that. Unless somebody has a calculator, Luke, you can break that down for me.
Okay.
But I think that's a prime number, I think.
Yeah, it doesn't break down. That's my guess.
No, thank you. You know, in my grade 9 applied class, we're doing fractions, and it's so great. Because they don't even want to do decimals. I have them forced into nothing with fractions. Okay, we get the idea of this? Callan, how you feeling?
So a dumb question. I don't know where those numbers came from.
Oh, what, 16 you mean? These ones here? Oh, sorry, it's not a dumb question. I'm glad you asked, because I'm just talking myself up here. I wrote up here that you're okay with this for negative 3, so I just added this, negative 9 plus negative 2
Okay.
plus negative 5.
Yeah.
And please don't be afraid to ask, guys. I'd rather you know now rather than trying to do it tonight on your homework and you have no idea what's happening. All right, here we go, dot product in 3 dimensions. Don't you guys find, say, the questions are just leaking off the page? Come on, come on, come on. You don't want to redo it for 10 years. All right, so if vector A okay, I would like someone to be brave here and to read my mind and tell me what A dot B is going to be. Now we know what A dot B is in 2 dimensions, right? Somebody want to try and guess what it's going to be in 3 dimensions? Yes.
AX BX plus AY BY plus BZ BZ.
Yeah. Now I don't have a fancy cosine law proof like I did in 2 dimensions. Okay, but it's the same thing. We're just going to add the components together. That's all we're going to do. Right? And I'm gonna say one other thing here, and then I'll explain, and then we'll do some examples. We're gonna say two vectors are orthogonal in these weights. If A dot D equals 0. Now, before you freak out, where are my meter sticks? I'm going to show you what orthogonal vectors look like. No, they don't look scary. Orthogonal is like perpendicular, but in the third dimension. Okay, now, where this, you might say, well, how is that even possible? Okay, the problem is for vectors that are orthogonal, there's actually an infinite number of orthogonal vectors. Chris, I'm going to ask you to hold this up to the class in any direction, doesn't really matter which one. You can hold it up in whatever you want, okay? For it to be a perpendicular vector, don't move it. It's got to stay still now, though. Okay, to be orthogonal, it has to form a right angle. Okay? Now, where else could it form a right angle? Well, it could spin like this. There's another right angle. It could go down here. There's another right angle. It could, excuse me, it could go right there. There's another right angle. So you can see there'd be right angles rotated all the way around here, right? Can you see what I mean? Right? So there'd be, you sort of get the logic what I'm saying there. There's a whole bunch, as long as it forms a right angle somewhere on a plane, that's called orthogonal. Yes? Okay, there's lots. There's lots that are there. That's what I'm trying to get rid of that.
Oh, so it's just basically before in 2D, if they're perpendicular, it's just equal to 0?
Right on. It's the same rule as that. It's the same rule as that. So basically, yeah, perpendicular in 3D. Here we go, example 2. Okay. Now this is where this is where these are hard to visualize, okay? Because to visualize two 3D vectors here and find the angle between, you can't do cosine law, you have to rely on your calculator for this, okay? So, back from the previous examples, Michael and only Michael. Are you going to tell me, please, what cosine of theta is equal to back in the last part? You recall? From like our warm-up today and or yesterday. Like A dot. Yeah, what is it?
Yeah, it's like E dot over the magnitude of the
Very good. Okay. So if you take a look, that's again the same thing, and that's one we'll be using quite a bit in here. Now this is the very same thing we did before, but in 3 dimensions. I'm going to hit pause in the video and give you guys a chance to try this one for yourself right now. Okay, and again, this is just calculator work again. You guys can do this. I'm not worried about it. Example 3, we're going to move on to one of those Spider-Man questions. I don't know so much. What do you know, crap? No, not oh crap. I think you weren't even in my class when you did the Spider-Man question, I don't think. I think probably just these two guys. Who else? Austin would have been. Yeah, Noah would have been there for that. I guess Nicole would have been there too, yeah. Whatever else is yeah, you would have been there too, right? Okay, are you in 13 or 12? No, I know you were in grade 12. Are you in grade 13 or 12, Nathan? Yeah, 12. I'm in 13 for some reason.
I tried it with this last year.
Did you try the Spider-Man one?
One that you gave to her to do, and that was